Section 4.4, Properties of Definite Integrals. Southwestern College, Professor Maria Olivas. .4 Properties of Definite Integrals. Objectives. Use properties of definite integrals to find the area under a curve. Use properties of definite integrals to find the area between curves. Section 1, Properties of Definite Integrals. Given f of x is continuous over the closed interval from a to b, we have the following properties. Starting with our first property. So looking at our first property, I want you to notice that the limits of integration are the same in this integral. So this states the integral from a to a of f of x dx is going to be equal to 0. So this is going to be true whenever you have the same limits of integration. The lower limit of integration and the upper limit of integration are the same, and therefore the interval of integration would have a width of 0, making this equal to 0. Another way to think about this is that you're being asked to find the area underneath this function at a single point. If we were to draw a line going down from that single point, you're basically being asked to find the area of a line. And the area of a line, well, there is no area. Or you can also think of it as the area under a point has no area. Our second property, it says the integral from a to b of f of x dx is equal to the negative integral from b to a of f of x dx. I'm going to draw a cloud around this and draw a star right next to it just so that you make sure you memorize this. It's very easy to forget, and we've actually already used this property in previous sections, so I just want you to remember that. It's a very important property. So whenever we switch the limits of integration, it's just going to end up being the opposite value that we had originally. Our third property says the integral from a to b of k f of x dx is equal to k times the integral from a to b of f of x dx. So this basically states that we can factor out the constant k and it will not affect the value of the definite integral. Our fourth property, the integral from a to b of f of x plus or minus g of x dx is going to be equal to the integral from a to b of f of x dx plus or minus the integral from a to b of g of x dx. So for this one, if we are integrating a sum or difference of functions, we can break it up into separate integrals. So the sum or difference of these two separate definite integrals will be equal to the same value of our original definite integral. Number 5, I'm going to go ahead and draw a cloud around this. So the fifth property states the integral from a to b of f of x dx equals the integral from a to c of f of x dx plus the integral from c to b of f of x dx. So we're going to begin by drawing a picture to help visualize this property. I'm going to draw 2 coordinate planes. In one, I want to represent the left-hand side of the equal sign, and on the second one, I want to represent the right-hand side of the equal sign. So let me start off by drawing those 2 coordinate planes, which are going to focus in on quadrant 1. So here's going to be my first coordinate plane, and there's my second. Let's start off with the first coordinate plane that I drew. On the x-axis here, I'm going to label the x values of a and b, and I'm going to draw a non-negative function above those, and I'll be drawing vertical lines down, going down to the values of a and b. I missed the b mark, so I'm going to erase that tick mark that I drew for b so that it looks like it measures at the exact right spot there. Perfect. I'm going to highlight in yellow the left-hand side of the equal sign, and I'm also going to highlight in yellow the area under the curve that I drew here for my first coordinate plane. So this area here that I've highlighted in yellow represents the area, or that definite integral that we have on the left-hand side of the equal sign. I've erased my second coordinate plane, and what I'm going to do is I'm just going to go ahead and copy this image, or this first coordinate plane that I drew here with the graph of the function, and A and B and the area shaded in there in between that closed interval from A to B. And now that I have copied and pasted that image, what I'm going to do is I'm just going to go ahead and draw a little tick mark in between A and B and call that value C. Draw a vertical line going up straight to the curve of my function. And now you can see here the two regions that are separated by C. I'm going to color in from the region from C to B in green, so that you can see that if I were to add the yellow region from A to C and then the green region from C to B, I would get that entire total area that is under the curve from A to B. So we can rewrite the definite integral from A to B of f of x dx as two separate integrals and add those up, and it will give us the exact same value. Example 1. Given the integral from -1 to 3 of f of x dx equals 7, find A, the integral from -1 to 3 of 5 times f of x dx. Well, this is going to be equal to, we're able to factor out the 5, so it's going to be equal to 5 times the integral from -1 to 3 of f of x dx. I'm going to highlight the integral from -1 to 3 of f of x dx in yellow, the whole thing in yellow, and I'm going to highlight the part in the given part that says it's equal to 7 in green. I can replace that whole yellow part, that integral, with a 7. So that's going to be equal to 5 times 7, which is equal to 35, and we're going to box that in. And that's it. All right, I'm going to erase all my highlighting here that we did for that first part, for part A. Now I'm going to go to part B. Part B says the integral from 3 to -1. I'm going to highlight that -1, that limit of integration, in yellow. And the 3, I'm going to highlight it in green. So the integral from 3 to -1 of f of x dx is going to be equal to the negative integral from -1 to 3 of f of x dx. Remember that said that we can switch those limits of integration, and it would just be the opposite of that regular value. So then that's just going to be equal to a -7, and we can just box that in. So here for example 2, before I start reading it, there is an error, there is a typo. Between the y and the f of x, it should say equal sign, and it didn't, it had a minus sign. So I changed it to an equal sign. I drew an arrow pointing towards it, and then next to the arrow, I wrote equal sign, just so that there is no confusion. All right, I'm going to go ahead and read example 2 now. Example 2, find the area under the graph of y equals f of x from x equal to -2 to x equals 5, given the following piecewise function. F of x equals 2 if x is greater than or equal to -2 and x is less than or equal to 0, and f of x equals x plus 2 if x is greater than 0 and x is less than or equal to 5. So I'm going to go ahead here and draw a coordinate plane here, and on this coordinate plane I'm going to label from -2 to +5 with little tick marks on the x-axis with a scale of 1. I've circled x equals to -2 and x equals 5 in the instructions that were given to me, so that's why I'm using these values from -2 to 5. I've labeled my x-axis with an x, and I've labeled my y-axis with a y. So now I'm going to highlight in yellow the first piece of our piecewise function, the part that says f of x equals 2 if x is greater than or equal to -2 and x is less than or equal to 0. I'm also going to highlight on the x-axis the interval from -2 to 0, because that is where I need to draw that piece of the function, on that interval from -2 to 0. I'm going to go ahead and also draw little tick marks on the y-axis from basically 0 to 7 with a scale of 1. And I'm going to go ahead and draw the function basically y equals 2 from the interval from -2 to 0. And I've drawn a blue cloud around that first piece of my piecewise function. The second piece of my piecewise function says f of x equals x plus 2 if x is greater than 0 and x is less than or equal to 5. I'm going to circle the 0 and the 5 because those are important values for those endpoints of my line. I'm going to make a little table of values here with x and y, and I'm going to substitute 0 and 5 into y equals x plus 2. For the 0, I notice here x is greater than 0. Strictly greater than means it's an open circle, so I'm just going to remember to keep that in mind as I'm drawing my picture here for my graph. And then I also notice here for the 5, it says x is less than or equal to 5, so I notice that's going to be a closed circle on my graph. So let's go ahead and substitute these values. Y equals 0 plus 2 is going to just be equal to 2. And y equals 5 plus 2 is equal to 7. So we're going to get 0, 2 and 5, 7 for my two ordered pairs. So we can go ahead and just draw those here on the graph. And I'm circling also for the first piece where it says x is less than or equal to 0. I noticed that it was closed for our first piece there at 0, 2. So I don't even have to worry about drawing an open circle. And then 5, 7, which I circled those values on my table of values here, that's going to be closed, so I'm just going to go ahead and draw a closed dot there, point at 5, 7. Connect my 2 points here from 0, 2 to 5, 7. And there I can see the entire picture of my graph. I'm going to draw vertical lines coming down from 5, 7 and coming down from -2, 2. And I'm going to shade in yellow the enclosed region of the area that I'm trying to find. It looks like here I've got like two pieces here. I've got the piece from -2 to 0, which kind of looks like a rectangle, and then I've also have the piece from 0 to 5, which looks more like a trapezoid. All right, so now that I have my entire region shaded in, we can go ahead and find this area. I'm going to set this up by finding a definite integral. Before I set up the definite integral that I'm trying to find, I noticed that I could use a little bit more space here, so I am going to go ahead and lasso all the work I did here for finding my ordered pairs. I'm going to move that work over to the left-hand side right above my graph here. And that's going to give me a little bit more space. I'm also going to take my table of values and lasso that in and move it over to the left-hand side of my graph so I have more space. So now I'm going to write my definite integral, the integral from -2 to 5 of f of x dx. Well, I'm going to have to split this up into two separate integrals. So I'm going to write this as the integral from -2 to 0 of 2 dx plus the integral from 0 to 5 of x plus 2 dx. And I know I can do this based off of the properties of definite integrals that we discussed earlier. I can write this as the sum of two integrals, and that will still give me the area, the total area that's under this function. So looking at this definite integral, this will become 2x evaluated from -2 to 0 plus x squared divided by 2 plus 2x evaluated from 0 to 5. Let's go ahead and open up a square bracket, and inside we're going to write 2 times 0 minus 2 times -2 and then close the square bracket. And then we're going to add to that, open up a square bracket, 5 squared divided by 2 plus 2 times 5, and then we're going to subtract 0 squared divided by 2 plus 2 times 0 is just going to give me 0. So I'm just going to write minus 0 and close the square bracket. Open up a new square bracket for a new line here. 0 plus 4, close the square bracket, plus, open up a square bracket, 25 divided by 2 plus 10, close the square bracket. I'm going to write 1 under the 10 and multiply by 2 to the numerator and denominator to get a common denominator for that. And for our next line, we're going to have 4 plus, open up a square bracket, 25 halves plus 20 halves. And I can add those two now because I have a common denominator there. So 25 halves plus 20 halves is going to give me 45 halves. So we can now go ahead and write here that this is going to be 4 over 1 plus 45 halves. I need a common denominator for the 4 over 1, so I'm going to multiply by 2 to the numerator and denominator. And I'm going to get 8 halves plus 45 halves is equal to 53 halves. And I'm going to go ahead and box that in. That's going to be our final answer for that problem. All right. So now we're ready to move on to the second part of this section. So our second part, or part 2, is going to be on finding the area between curves. We're going to review the definition of the definite integral as area under a curve. So right now we have here two graphs. These are two identical graphs. We basically have the graph that's focused in quadrant 1. We have here a curve that represents the function y equals f of x. So we have the equation y equals f of x in the upper right-hand corner of the graph with an arrow pointing towards the curve, identifying that as the function. On the endpoints of this graph in quadrant 1, we have two dashed vertical lines that go down to the x-axis. And that basically represents the graph that we are seeing right now. What I'm going to do here is I'm going to go ahead and represent in the first graph how we began finding the area under a curve. If you recall, we began using Riemann sums to find approximations for the area under a curve. We did that by taking the area that was under the curve and partitioning it into a series of rectangles, and then finding the sum of those areas of those rectangles would give us an approximation for the area under a curve. So I'm going to go ahead and draw one of those rectangles here to remind us how we found that area. So here is one of these rectangles that we use when we're finding Riemann sums. I'm going to shade it in. And the way we found the area inside of this rectangle, we needed to multiply the height times the width. The width of this rectangle, why don't we call it delta x? And the height, let's go ahead and call it f of x sub I. And I would multiply the height times the width, and that would give me the area. On the graph that is on the right-hand side here, which is identical to the graph that was here that I just drew my rectangle on, I'm going to go ahead and shade the area under this curve in yellow. And this is going to represent when we were able to find definite integrals to get an exact area under a curve. I'm going to go ahead and label the x values here from a to b, the closed interval from a to b where this function is drawn. And then I forgot to write down how we found the area of that first rectangle here where it says area of a rectangle, so I'm going to write that in right now, f of x sub I times delta x. And that's how we found the area of that first rectangle. Now to represent the approximation of the area up above using those rectangles, we would represent this as the summation from I equal to 1 up to n of f of x sub I times delta x. And that would give us the approximation of the area up above, right, using those Riemann sums. If I wanted the exact area, I could represent this as a limit. The limit as n goes to infinity of this summation, which is also equal to the definite integral from a to b of f of x dx, which represents the picture that I have written right above this integral that I just wrote down, right? So That's how these pictures that we drew up above tie in to what we have written underneath. All right, now that we have reviewed the definition of a definite integral, let's move on to this important idea. Here we have a vertical line segment with the endpoints at x sub 1 comma y sub 1 and x sub 2 comma y sub 2. If I want to find the vertical distance on this line segment, the important part to focus on here would be our distance from the y's. So I'm going to refer to that as delta y. In order to find that distance, delta y is going to be equal to y sub 2 minus y sub 1. This delta y is going to represent an exact distance for us. Now let's imagine I'm trying to find the distance between two functions. If I have an upper function and a lower function, let's say my upper function is f of x, and I want to find the distance from, say, a lower function, let's call that one g of x, then I would subtract those two. F of x minus g of x would give me the distance between those two functions. And that is exactly what we're going to do here when we're trying to find that area between curves. So in order to find that vertical distance, I am going to have my upper function minus my lower function. So here my upper function is referring to my f of x, and my lower function is referring to g of x. So here we have our graph, and you can see here on our graph, we have a graph, a coordinate plane with two functions on there. Y is equal to f of x represents the upper function. I am highlighting the upper function in green. And then we also have here y equal to g of x is going to be equal to our lower function. And I'm going to highlight that lower function in blue. And I'm also going to highlight the y equal g of x in blue and the g of x that I wrote up above and the lower function part that I wrote also in blue. I'm going to draw a rectangle here in between these two functions, so that we can imagine what it would look like if I were to draw several rectangles here and partition this area into several rectangles. I'm going to shade in that rectangle, and we can imagine, right, that width right here, that's going to be represented with delta x. And then the height of this rectangle, that's going to be represented by subtracting the two functions. So that's going to be f of x minus g of x. So in order to find the area of this rectangle, I need to multiply the height of the rectangle with the width. I'm going to just go ahead and highlight everything here in between two curves and in between the two functions to represent the entire area that I'm trying to find here. And I've highlighted all of that in yellow in between the two functions. And then I've also written down here, I put little tick marks, and I've written A for my first x value and B for my ending x value to represent that closed interval where these two functions are contained. So we would find that area, let's call it A, by writing A equals the definite integral from A to B of f of x minus g of x dx, where f of x represents my upper function, and then g of x represents my lower function. And I've written the word upper function above f of x with an arrow pointing towards it, and I've written the words lower function above g of x with an arrow pointing towards it. I'm going to go ahead and box in that definite integral. And that's going to be what we're going to be using to set up our integrals for the next problems. All right, so these examples, we're going to set up integrals to find the indicated areas. You do not need to evaluate the integrals. Number 3, the area of the region bounded by y equals x squared plus 2, comma, y equals negative x, comma, x equals 0, comma, and x equals 1. We're going to begin by drawing a picture to represent this. If we have a visual, it's going to be much easier to come up with that integral. So I've drawn a coordinate plane here. On this coordinate plane, I'm going to draw tick marks on the y-axis. I'm going to go up to here to positive 2 on the y. And then I'm going to draw a sketch of y equals x squared plus 2. And it has an x-intercept at 0, 2. And that's going to be a parabola opening upward. And then for y equals negative x, and I've circled that equation, I'm going to draw a line with a negative slope. And the y-intercept of that linear equation, or that line, is going to be at 0, 0. So I've drawn a point at 0, 0. And I've gone down 1 and over 1 for the slope. And now I'm going to connect my two little points that I've drawn here with a line. Now I've also circled the equations x equals 0 and x equals 1. I'm just going to go ahead and draw line segments connecting from the parabola down to the line to represent those equations, those lines. And I'm going to go ahead and shade the enclosed region of the area that I'm trying to find in yellow. So now that I have this visual, it's going to be much easier for me to set up my integral. This upper function, or the parabola that's opening upwards, I'm pointing an arrow towards it, and I'm writing down the equation y equals x squared plus 2 to it, and that's going to represent my upper function. Now my lower function is going to be represented with our line y equals negative x. So I'm going to point an arrow towards that line, and I'm going to write down the equation y equals negative x, and I'm going to also write down the words lower function next to it. Now that we have those labeled, we can set up our definite integral. So we're looking at this between the closed interval from 0 to 1. So this is going to end up being a equals the definite integral from 0 to 1 of, and remember we need to write down our upper function first. So I'm going to open up a set of square brackets. I'm going to open up a set of parentheses. I'm going to write x squared plus 2, close the parentheses, and then go minus, open up a set of parentheses, negative x, and then close the parentheses and close our square brackets, and don't forget your dx. So now we can simplify this a little bit. A is going to be equal to the definite integral from 0 to 1 of, I'm going to open up a set of parentheses, x squared plus x plus 2, close our parentheses, and dx. And that's going to represent our definite integral, so I'm going to box that in. And that's all we need to do. We do not need to evaluate this integral for this problem. Number 4, the area of the region enclosed by y equals x squared, comma, y equals 6 minus x. So I'm going to go ahead and draw my coordinate plane. This coordinate plane is going to focus more on quadrant 1 and 2. I'm going to go ahead and draw my parabola. So we have a parabola that opens upwards, and it has its y-intercept at 0, 0. So I'm just going to go ahead and draw a sketch. It doesn't have to be perfect. We're doing this for the visual to help us set up the integral. So this represents y equals x squared. I've circled my equation, and now I've also circled y equals 6 minus x. And this is going to be written as y equals negative x plus 6. That way it looks more like slope-intercept form. I can see that my y-intercept is at 0, 6, and it has a slope of negative 1. So I've drawn tick marks on the y-axis going up to 6 with a scale of 1. And I've drawn a dot or a point on 0, 6, and then I've gone down 1 over 1 and drawn another point, and I've drawn my line. I can see here that my line is my upper function. My parabola is going to be my lower function. So I'm going to go ahead and shade in that region in between the two functions in yellow so that it stands out and we know exactly what we're trying to set up an integral for. We're trying to set up a definite integral that will find us the area bounded by these two regions, by these two functions. I'm going to draw a point, a red point, right where the two functions intersect on both ends. And I'm going to draw a dashed line going down to the x-axis. And I'm going to label those x values as, I've put B and A, but you know what? I'm going to erase those. We're actually going to write this as x equal to, and we're going to have to find that exact x value. So in order to find that exact x value where those two functions intersect, I need to find the points of intersection for this problem. So I've gone ahead and circled the x squared and the 6 minus x in the equations, and I wrote x squared equals 6 minus x in order to find my x. I've gone ahead and I subtracted 6 from both sides, and I've also added x to both sides. So this is going to give me x squared plus x minus 6 equals 0. We have a quadratic equation. In order to solve this quadratic equation, I am going to factor this. So this is going to factor into x plus 3 times the quantity x minus 2. And that's going to be set equal to 0. I'm going to set each one of these factors equal to 0, and I'm going to solve. So let's go ahead and set this up. We're going to write x plus 3, set it equal to 0, and x minus 2, set it equal to 0. And then let's solve each one. For the first equation, I'm going to get x equal to negative 3, and the second one, I'm going to get x equal to positive 2. That tells me my x values here, where these two functions are intersecting. So I went ahead and wrote x equals negative 3, and x equals negative 2 for my two sets of dashed line segments that I drew here connecting where the functions intersect down to the x-axis. I'm also pointing an arrow at my upper function, my line, and I wrote the words upper function and y equal to 6 minus x. And I drew an arrow pointing to my lower function, the parabola, and I wrote y equals x squared, and I wrote the words lower function. So that way there's no confusion here. We know exactly which one represents our upper function and which function represents our lower function. So when we set this up in the definite integral, we're doing it in the correct order. I'm going to go ahead and take my work that I did here for my points of intersection. I'm going to make it smaller, and I'm going to move it so that I have more space to do my work. So I moved it slightly to the left. I drew a vertical line separating the work from my points of intersection, and now on the right hand side I'm writing a equals the definite integral from negative 3 to 2. I opened up a set of parentheses, 6 minus x, close the parentheses, minus, let me just add a square bracket before the first set of parentheses, and then we had minus x squared, close the parentheses, close the square bracket, dx. Next line, a equals the definite integral from negative 3 to 2. Open up a set of parentheses of negative x squared minus x plus 6, close the parentheses, dx. And now here, this is going to represent my definite integral. I'm going to box that in. And once again, we don't need to evaluate this. We just needed to set this up. And we're done for that one. Number 5, the area of the region enclosed by y equals the square root of x, comma, y equals 1/4 x. So let's go ahead and set this up. Let's start off by drawing a coordinate plane. Okay, so here is my coordinate plane. I've got y equal to the square root of x, so I've gone ahead and drawn a sketch to represent y equals the square root of x, starting at 0, 0, and then it goes off to the right, and then y equals 1/4 x. I've labeled my ordered pair 0, 0. I'm drawing tick marks on the x-axis up to 4 with a scale of 1, and I have drawn a point at 4, 1. And this is going to represent my line, y equals 1/4 x. Okay, I think I missed my point a little bit there, so I'm going to have to fix my point just a little bit. So I erased that first point that I did there. You guys know that it crosses at the point 4, 1. I am going to go ahead and shade the region that is enclosed by the two functions. So now that I have shaded in that region, I've shaded the region in yellow. I can tell that this region that I'm looking for the area in is focused in quadrant 1. I already know that one point of intersection is going to be at 0, 0, and the other one here, I drew a point at the intersection for my second point, and I drew a dashed line coming down to the x-axis. I'm not sure what that x value is. So what I need to do is I need to find that point of intersection. Let's go ahead and find that point of intersection. I drew an arrow pointing to that point of intersection, and I wrote point of intersection. I actually already know the first point because that one was at 0, 0. I need that second, just the second point in this case. So I'm going to go ahead and set my two equations equal to each other. I'm going to set the square root of x is going to be equal to 1/4 x, and I'm going to solve this equation. I'm going to square both sides of my equation. Square root of x squared is just x, and that's going to be equal to 1/4 x all squared is going to be 1/16 x squared. I'm going to subtract x from both sides, and I'm going to get 0 equals 1/16 x squared minus x. Here we have a quadratic equation that's set equal to 0, so I can go ahead and solve this by factoring. Before I start factoring, why don't we go ahead and multiply through this equation, both the left-hand side and the right-hand side, by 16 in order to get rid of this fraction that we have in front of the x squared. So let's go ahead and do that. We're going to multiply the left-hand side and the right-hand side of the equation by 16. So I'm going to write here 16 over 1, and I'm going to multiply every single one of these terms, both on the left-hand side and the right-hand side, by 16. We're going to end up with 0 equals x squared minus 16x. Now I'm going to factor out an x, so I'm going to have 0 equals x times the quantity. We're going to open up a set of parentheses, x minus 16, and close the parentheses. And this is going to give us two equations, x equals 0 and x minus 16 equals 0. And if we add 16 to both sides, we will get x is equal to 16. So my two solutions here are x equals 0 and x equals 16. I already knew the x equals 0 part. The x equals 16 was the one I was missing. I was missing that x value. So I've gone ahead and labeled 16 on the x-axis, right where my dashed line meets the x-axis from that point of intersection. My integral is going to be a equals the definite integral from 0 to 16 of, we're going to open up a set of parentheses and write square root of x. And I'm writing over here on the graph with an arrow pointing to my upper function. I labeled the equation y equals the square root of x, and I wrote down the words upper function. And then for my line that's underneath, I drew an arrow with the equation y equals 1/4 x, and also another arrow pointing at it saying lower function. Going back to my definite integral, we're going to subtract 1/4 x, close the parenthesis and write dx, and box that in. And we're all done with that one. Now let's go ahead and evaluate number 5. So I'm going to write a equals the definite integral from 0 to 16 of, open the parentheses, square root of x minus 1/4 x, close the parentheses, dx. So we're ready to integrate this. you know what, I've gone ahead and I've erased my square root of x and I rewrote that as x to the 1/2 power because that's going to be easier to integrate. So this is going to be x raised to the 3/2 power divided by 3/2 minus, here we're going to have x raised to the 2nd power divided by 4 times 2. And then this is going to be evaluated from 0 to 16. This is going to be equal to 2/3 x raised to the 3/2 power minus x squared over 8 evaluated from 0 to 16. And I'm drawing a vertical line here separating my work from evaluating this definite integral and the work that I had done previously where I was finding those x values for those points of intersection. All right, our next line is going to be, we're going to open up a square bracket. This is going to be equal to 2/3 times 16 raised to the 3/2 power minus 1/8 times 16 raised to the 2nd power. Close our square bracket. Minus, this is going to be 2/3 times 0 raised to the 3/2 power minus 1/8 times 0 raised to the 2nd power, close our square brackets, and that will be equal to 32/3. And just go ahead and do this on your calculator, you know, when you get to this point so you can get your answer. And I'm just going to go ahead and box in that answer of 32/3. And we are done for that problem. Example 6. Find the area of the shaded region. Here on the right-hand side, we have a coordinate plane where the x-axis is labeled from -1 to 3 by a scale of 1, and the y-axis is labeled from -2 to 1 by a scale of 1. We have the function y equals x to the 4th minus 2x cubed graphed on the coordinate plane. The shaded region is represented in quadrant 4. The shaded region is above the graph of y equals x to the 4th minus 2x cubed, all the way up to the x-axis, and between x equal to 0 and x equal to 2. I have gone ahead and drawn a rectangle within the shaded region to represent one of those rectangles we were drawing when we found Riemann sums, and I am shading in that rectangle. I've also highlighted in green the function in quadrant 4 and the y equals 0 graph, or the x-axis. The y equal to 0, that's going to represent our upper function, and our lower function is going to be y equals x to the 4th minus 2x cubed. Now that we have those labeled, I'm going to go ahead and set this up as a equals the integral from 0 to 2 of open parentheses upper minus lower close parentheses dx. So this is going to be equal to the integral from 0 to 2 of open a set of square brackets 0 minus open a set of parentheses x to the 4th minus 2x cubed. We're going to close the parentheses and we're going to close the square brackets and write dx. This is going to be equal to the integral from 0 to 2 of, I'm going to write a negative in front of a set of parentheses. Inside the parentheses we have x to the 4th minus 2x raised to the 3rd, close the parentheses, dx. This is going to be equal to a negative times the integral from 0 to 2 of, open up a set of parentheses, x to the 4th minus 2x to the 3rd, close the parentheses, dx. And this equals a negative times, we're going to open up a set of square brackets, x to the 5th divided by 5 minus 2x to the 4th divided by 4, close the square brackets, and we're going to evaluate this from 0 to 2. And this will be equal to a negative times, open up a set of square brackets, open up a set of parentheses, 32 over 5 minus 8. Close the parentheses, minus 0, and then close the square brackets. And this is going to be equal to 1.6, and we're just going to box that in.